A very good afternoon to all of you. Now, today in this class, we are going to continue with the task of revision that we took in the last class. Remember, we were talking about sound intensity and sound wave. In the last class, we saw sound as a pressure fluctuation and we saw the sound as displacement fluctuations, and we could obtain the equation for the displacement wave and the pressure wave, and we could also get an expression for the maximum pressure amplitude. So today in this class we are going to talk about sound intensity further, decibel scale, normal modes of vibration in the instruments, and interference of sound, beats, and Doppler effect. So let's go ahead. Am I audible clearly? I suppose I should be. Am I audible clearly? Yeah, so at least I can hear myself, so it's fine. I suppose even others could do. So let me go ahead. Thank you, Namishka. Thank you, Simran. So, what is sound intensity? We all know the intensity of any physical phenomena. The same definition applies to sound intensity. The wave intensity, which is generally represented by I, is equal to the time average rate at which the wave energy is transported per unit area across a surface perpendicular to the direction of propagation. So if the wave is moving in a given direction, all you need to keep is a surface which is perpendicular to the surface of propagation of wave, and you figure out that how much energy is passing per unit area per unit time. That gives you the wave intensity. Now this is true for all types of waves: electromagnetic, mechanical, longitudinal, transverse, etc. So do remember that. So intensity can be defined as energy flowing per unit normal area per unit time. Remember, the normal area is important. It's a kind of flux. The unit you can easily guess. This unit is joule, this unit is second, this is meter square. So joule per second meter square. Joule per second is nothing but power, that is watt. So this is watt per meter square. So unit of intensity is watt per meter square. Now, although this derivation is not the scope of revision, but do remember that intensity of the wave, especially the intensity of longitudinal wave, is the time average of the product pxy in p into vy. P is the pressure fluctuations while v is the particle velocity. So the product of the two, if you average out over a large interval of time, it gives you the intensity of wave. Of course, your reference book derives this. As I said, I'm doing a very quick revision, so derivation is not in the scope right now. But do remember, because this is needed for the next step. So I can figure out what is my particle velocity. Particle velocity is derivative of the particle position. Particle positions, we have seen, it is a cos kx minus omega t that we saw in the last class. Take a derivative of a cos kx minus omega t and you get omega a sine kx minus omega t. So this gives you the particle velocity. The symbols represent their usual meaning. We remember k is 2 pi by lambda, wave number. Omega is 2 pi by 2 pi f or 2 pi by t, the angular frequency. So the product of the pressure wave and the velocity wave comes over here. So pressure wave equation was bka sine kx minus omega t. The velocity, particle velocity, is omega a sine kx minus omega t. You multiply the two together and you get an equation which is b omega k a square sine square kx minus omega t. Now this is the instantaneous value of the product. We have just argued that intensity is nothing but an average value of this product. Okay, so if you take an average of this, you will find that this part is a constant. This does not change with time. Only factor that changes with time is sine square of this time function. But the sine square of any function averaged out over any function of time averaged out over a long interval of time will give you 1 by 2. So your intensity of sound will become 1 by 2. B is bulk modulus, omega is angular frequency, K A square. So this becomes your intensity. I can use the standard formula. Omega is equal to V into K. Remember that V is the wave velocity and K is the angular wave number, 2 pi by lambda. So omega is V into K and V square is B by rho. This also we saw in the last lecture, where the velocity of sound in a medium is given by under root of the modulus of elasticity divided by density. So if you square, you get V square is equal to B by rho. So I can use these two in this equation back, and I get intensity as half root rho B omega square A square. Now the important thing that you have to notice from here is this, that intensity is proportional to the square of the amplitude. Do remember, intensity is proportional to the square of the amplitude, and intensity is proportional to the square of omega, that is frequency. So these two things you have to remember, because in SYBSC our discussions will revolve around this point, that as the sound changes frequency, the intensity will vary. So do remember, and of course all interference and other experiments, they involve this parameter that I is proportional to A square. Okay, you can put P max value in this and you get I in terms of P max. So that is another equation. Do remember that if it's a free space, that means if you have a point source of sound and the sound spreads out in all possible directions uniformly, then the intensity is proportional to 1 over R square. But if it is not a free space, suppose if you are close to a surface, or if it's not a point source, it's a linear source, etc., etc., then the sound does not drop as 1 over R square. Then it has some other parameter. Generally, it drops slower than 1 over R square because there are reflections and all, and we will discuss those topics later when we start with SYBSC part. I'm throwing in some problems over here. These problems are taken from the reference book and you can solve it. But this is, yeah. Sound intensity varies. Sound intensity of different day-to-day objects, day-to-day phenomena can vary from a very low value to a very high value. Now, how much low is really low? So in terms of watt per meter square, the threshold of hearing at 1000 hertz is 10 power minus 12. That means if you have a 1000 hertz sine, if you have 1000 hertz, if you have 1000 hertz signal and if its intensity is as less as 10 power minus 12 watt per meter square, then you would be at least be able to hear it. Remember, when I say threshold of hearing, I am talking about an average over many people. Threshold of hearing varies from person to person and from region to region. Example, if you are in a very noisy environment, if you live in a very noisy environment, then your threshold of hearing is generally little high. If you are in a village or in a countryside, or if you're mountainous terrain, if you live, your threshold of hearing is further low. So it depends on where you live. So we take this figure as an average of a large number of people's threshold of hearing, and that we have fixed it as 10 power minus 12 watt per meter square. Now, as you go higher, you can see different phenomena will give you different intensity values. So, if you have a quiet radio at home, I really don't understand what is meant by quiet radio. I assume that it's a radio set which has been played at a low volume, because if it's quiet, then if it's not playing at all, then it doesn't matter. uh, Quiet automobile, I feel that it's an automobile which is where the ignition has started but it is not running on the road. So these are the intensities. Busy street traffic is 10 power minus 5. Ordinary conversation, uh, 3.2 into 10 power minus 6. Then your threshold of pain is 1 watt per meter square. So, and military jet aircraft 30 meter away is 10 power 2. So you can see that it could be very painful if your military jet is flying close to you, and that is why generally all airport operations, a distance is maintained between the aircrafts and the general people. And the people who work close to the aircraft, vicinity of the aircraft, they always wear the headphones now these days, which are noise cancelling, which will reduce the noise further. So you can now see that this has a large variation in intensity. Radio played a quiet place where no other sound interferes. Yes, Jay, it could mean as well. I mean, you don't play radio at a very loud volume, and you play at a place which is in general quiet, because it is slightly above the whisper and less than the ordinary conversation. So maybe that way. The book is not very clear that what do they mean when they say quiet radio or quiet automobile. So yeah, we are free to take our interpretations unless you measure it. So this variation is huge and sometimes difficult to write down, difficult to tackle with, and therefore we have converted this into a logarithmic scale, and that is what we call as decibel scale. So this is how the decibel scale is converted. Present day mobile phones offer so many apps which acts like decibel meter. There is one app from Google Lab or Google Scilab or something like that, that offers a good decibel meter. I would encourage you people to check that app because you might need it for your computational work. Other apps are Audacity. If you can download and start working, learning that also, it will be helpful. So how do we get the decibel scale? So remember, any intensity value we take, we divide it by the peak intensity value. So this ratio, so I'm doing a comparison, it's a comparative scale. You don't, a decibel value does not represent the absolute value of the sound. It only gives you that with respect to the reference intensity, which is the threshold of hearing, how much loud another intensity is. So that is what it gives. So you take this ratio and you take log to the base 10 of this ratio, multiply by 10, and you get a value which we call at sound intensity level. Remember the level word, if it comes, that means I'm talking in the decibel scale. I'm not talking in terms of watt per meter square. So do remember that. So if I convert these figures into decibel, this is what I will get. So 10 power minus 12 itself will become 0. And then you can see that for every uh, 10 times difference, you just add 10 here. So from 10 power minus 12 to 10 power minus 10, it is 100 times more intense. You add 20 in your decibel scale. If it is 10,000 times more intense, you add 40 in your decibel scale. So decibel scales are very easy to write, comprehend, understand. You get rid of these minus indices, you get rid of multiplication, etc., etc. It gets simplified. And that is why most of the time the decibel indices are used. The other example of this kind of calculation is a richer scale. Do you know what is a richer scale? I hope geology student at least must have heard about it or must have used it. It is a scale to measure and classify the intensity of earthquakes. So again, that is a logarithmic scale. So if you are 6, if you go 10 to 20, you go 10 to 100 times more. But I think that scale is designed slightly differently. So, we can talk more in detail about that scale later on, because if you go from 4 to 8, the severity of earthquake increases many folds. So, yeah, so come back to this. So this is the decibel scale. So as I said, I'm throwing some problems here which are taken from the reference book. You can try to solve it. They are solved examples, so solutions are given. We are all familiar with standing waves. Standing waves on sonometer, standing waves on guitar string, transverse standing waves, we are well familiar. Just as there are transverse standing waves, there are longitudinal standing waves as well. So here is one example. I have a speaker which is uh, emitting sound towards a wall. The sound travels to the wall, gets reflected from the wall and travels back to the speaker. Now in this case, there are certain points where the oscillations will cancel out and you get notes. I'm talking about displacement notes. And there are certain points where the oscillations will not cancel out and they will be maximized rather, and those points are called antinodes. So we are all familiar that this is distance between a node and antinode is lambda by 4, and distance between two nodes or two antinodes are lambda by 2. So you can measure different distances at different wavelengths, and at some point if you don't hear any sound, for example here you will hear a loud sound, while at this point you will hear a loud sound, at this point you may not hear any sound. So if that happens, then you can find which is antinode and which is node, and from that distance you can calculate lambda. So the two type of equations that you have encountered are these two, open pipe and stopped pipe. Remember, when I say open pipe, it is a pipe which is open at both the ends. If you have any pen paper, please note it down. If you say open pipe is open at both the ends. Stopped pipe, what does it mean? Stopped pipe is something which is stopped at one end. So when you say stopped pipe, it is not stopped at both ends. Please be careful. Most of the problems will use this terminology: open pipe, stopped pipe or closed pipe. So when we say closed pipe, we say it is closed at one end, not at both the ends. So if it's open pipe, then the normal modes of vibrations of NV by 2L, where N is an integer whose values vary from 1, 2, 3, 4. V is the velocity of sound in the medium. L is the length of the pipe. Now N is 1, 2, 3, 4. It shows that all the harmonics are present. You also know that the first harmonic is called fundamental, and second is called first overtone, third is called second overtone, so on and so forth. What happens in this case? If it's a stopped pipe, then it is N is 1, 3, 5. That means only odd harmonics are present. Here also, when you say N is equal to 1, that is fundamental. And then when you say N is equal to 3, then N is equal to 3 is the first overtone. N is equal to 5 is the second overtone. Yes, Tejas, you said it correctly. Stopped pipe is open at one end. So I have two examples over here. This is a musical instrument. It could be flute, clarinet, whatever. We are going to discuss these instruments later on in detail, little bit more detail. But this is what we have done in FY already, that it is open at one. This end is open, so this is always considered as an open end. At an open end, you will always get an antinode because the molecules, the air molecules, medium molecules gets lot of free space to oscillate. So an antinode here. If the other end is also open, then an antinode here, and this is an open tube. A closed tube, this end is considered open, but this end is blocked, stopped, or closed. You can see that. So at a closed tube, always a node is formed because the molecules are not free to move. So here you get a node. So here in the fundamental mode, you can see that this distance is lambda by 2. I'm sorry, this distance is lambda by 4. This distance is also lambda by 4. Total is lambda by 2. Here, this large distance is lambda by 4. So that is why here you get 2 in the denominator and here you get 4 in the denominator. And these are my normal modes. This is one mode of oscillation. The next, here you get a node here, an antinode, and antinode here. This is my next mode of oscillation where you get an antinode, node, antinode, node, antinode. And this is my next mode of oscillation. If you do a more critical analysis, you will find that this is 2 times F1 and this is 3 times F1. While here F1 is V by 4L, this is 3 times F1 and this is 5 times F1. So these are more normal modes of vibrations that we have learnt. Firstly, I think in 12th standard, and it was there last year as well. So if you have left it as an option, one reading would be sufficient. Again, I'm throwing some questions. Then we are familiar with resonance also. If you recall your 12th standard sonometer experiment, what did you used to do? Or resonance tube experiment, क्या करते थे आप? So you used to take a tuning fork and keep it over the tube, or you used to keep it over the sonometer wire, next to the sonometer wire. And what it used to do? It used to force the other body to oscillate. The tuning fork in sonometer forces the wire and the bridge and the system to oscillate. The tuning fork in resonance tube experiment forces the air column to vibrate. You can do a simple experiment like this. This is a pipe and this is an speaker. You are driving the speaker with different frequencies. This you can do using your mobile also. So you can use your one headphone to generate different frequencies from any app generator app, feed it to a tube live, and use another mobile's microphone to sense that what frequencies it is oscillating. So it will force this pipe to get into resonance at different frequencies. So F1 is fundamental. Then since this is open at both the ends, you get F2, F3, F4, all the fundamental frequencies it will appear. Whenever the speaker hits a fundamental frequency, you will find that sound intensity has increased because amplitudes will rise. And the moment you deviate from that frequency, sound intensity will drop slightly. And again, it will increase and it will drop. So we are in a very great situation to do these kind of experiments. Remember our college, it's very noisy at times, but at your home, I'm sure you will have some quiet moments and some time of the day or in the night. And at the time at which you can perform these kind of experiments. So these are the normal modes of vibrations which can be checked practically by a typical resonance experiment. So going ahead, interference of sound do interfere just like light. In light you have done interference of light, Newton's ring, etc., etc., bright band, dark band. In sound you get maxima or minima. A typical setup looks like this. You have an amplifier that is driving two speakers and you have a microphone at some distance. So when the microphone is here, you can see that it is equidistant. So the part difference between the two waves is zero, and you will mostly hear a maxima because the sound is coming in phase. Now if you go to some other position which you can calculate, because sound in wavelengths are measurable in centimeters and meters, so it's very easy to find out some other position where the distance is changed by lambda by 2. The path difference between this path and this path is lambda by 2, and you get a destructive interference, and you will hear a very less sound or no sound at all. So by varying the position of the microphone, you can find out the positions of maxima and minima, and you can do an experiment which is analogous to double slit experiment in light. What are the conditions for constructive and destructive interference? Let's check. For constructive, they should be in phase and the path difference should be n lambda, where n takes value 1, 2, 3, dot, 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 etc. And destructive interference, they should be out of phase. The path difference should be 2n minus 1 lambda by 2. N takes value 1, 3, 5. Remember this. Only odd multiples of lambda by 2. So 1 lambda by 2, 3 lambda by 2, 5 lambda by 2, 7 lambda by 2. Even multiples of lambda by 2 are here. So if you say 2 lambda by 2, 2, 2 will cancel. It will become 1 lambda. And if you say 4 lambda by 2, then 2 2s are 4. You get 2 lambda here. So path difference has to be odd multiples of lambda by 2 for destructive interference. Path difference should be n lambda for constructive interference. Then we have done beats also, beat phenomena. It's very straightforward. We have learnt beats is very important phenomena in psychoacoustics because beat helps us to understand the human response to two tones which are closely placed. I have two frequencies which are very close, the red one and the blue one. They are not identical, but this differs with very small number in their frequency. Now, if I play them together, then I do not hear them separately. And that's the key thing. Human ear cannot distinguish between them. So it is one of the key experiment by which we determine the sensitivity of human ear to the separation between two frequencies. By playing them simultaneously and changing one, we can figure out that one's ear is how much sensitive to delta f, that is difference between two frequencies. So yeah, if the frequencies are very close, you don't hear them independently, but what you hear them is a alternate maxima and minima, which is called beat. Like one minima, maxima, minima. One this group is called one beat. Just like somebody is beating a drum at some frequency. So you get beat, and that's why the phenomena is called formation of beats. And the frequency at which the beats are formed is called beat frequency, and beat frequency is, you all know, it's mod of fa minus fb. It's to be very strict. You find the difference between the two. So it's actually a mod of fa minus fb, the two frequencies. The sound produced is the average of the two. Do remember, the frequency of the sound at which the beat will happen is the average of the two. So you have to be careful. For example, if you have 100 hertz and 102 hertz, then you will get 2 beats per second. But these 2 beats are of the frequency 101 hertz. So this you can try. You can take any two sound sources. Don't play two apps on the same system, either on your laptop, one on your laptop, one on the mobile, or two different mobiles, or one mobile and one ipad or something like that. Take any two sources, generate two sound frequencies, try to match the frequencies close enough, and then listen to the results, and you will find that they beautifully produce beats. So that is one beautiful thing that again you can do at home. We are all familiar with Doppler effect. Remember, it's a change in the observed frequency or listener's frequency fl if the source is moving, or the observer is, or the listener is moving, whoever. So suppose if I have a source which emits the frequency fs, and I have a listener which is moving with the velocity vl, and the source is also moving with the velocity vs, then the what listener will hear is v plus vl upon v plus vs into fs, where v is the velocity of sound in the medium. So this is how the entire formula is based. Here I am assuming, and do remember carefully, here I am assuming that the source is going away from the listener and listener is moving towards the source. So in this formula, it's a very inherent assumption, and this assumption is made in the reference book. I'm carrying the same one. When I write this formula, the source is moving away from the listener and listener is moving towards the source. It's like a car making a siren going ahead. You are in another car as a listener chasing the first car, something like that. If reverse happens, then these signs will reverse. So if the source starts moving towards the observer, then this will become minus. And if the listener starts going away from the source, then this will become minus. So do remember that Doppler effect is very useful, used at many places. One of the important places is to sense the speeds of the vehicles. So you will find them at the traffic signals or highways, expressways, where the speed of the vehicles can be checked. They do not overspeed the given speed limit. Any speed of moving objects. For example, if a cricket match is on, then the speed of the ball can be determined by Doppler torch. Tennis match is on, then the speed of the shot can be obtained by Doppler torch, etc. So very useful phenomena. Doppler effect happens in light also, which has a slightly different form, and I'm sure you must have done it in the other courses, that involves red shift and blue shift. But the fundamental idea remains the same, that if the source is coming towards the observer or observer is going towards the source, then the observed frequency is greater than the original frequency. And if they are going away from each other, then the observed frequency is less than the original real frequency. So here are some problems. So maybe we can stop here. Thank you.